Welcome. There is nowhere to be right now, nothing to solve, nothing to hold on to. Let your shoulders sink into whatever is beneath you. Let your breath find its own unhurried rhythm, in and out, like tide against a shore that has nowhere else to be either. Tonight we drift through light itself, its speed, its limits, its strange constancy, and let the vastness of it carry you gently toward sleep. Light travels at 299,792,458 meters every second through empty space. That number has stayed fixed since before there were eyes to see it. It is fast enough to circle the Earth about 7 times within a single second. Yet across the vastness between stars, even this speed becomes a slow, patient traveler, carrying its message for years before arrival. The speed of light is denoted by the letter c, a small mark for something so enormous. Physicists chose it long ago, likely from the Latin word celeritas, meaning swiftness. It appears quietly inside equations that describe stars, atoms, and the shape of time itself. One letter, tucked between numbers holding the architecture of the universe together. Nothing that carries mass can ever reach the speed of light. As anything with mass moves faster, it requires more and more energy until the amount needed becomes endless. Photons themselves have no mass, which is precisely why they alone can travel at this ultimate pace. Everything else, planets, dust, even the faintest breath of gas, must always fall short. The speed of light stays the same for every observer, no matter how fast they themselves are moving. A person standing still and a traveler rushing past at tremendous speed will each measure light arriving at exactly the same rate. This still feels strange, even now, defying the way ordinary speeds are supposed to add together. It is one of the quiet oddities the universe simply insists upon. Albert Einstein built his special theory of relativity on this one steady fact, that light speed never changes for anyone. From that single foundation, strange and beautiful consequences followed: time bending, space stretching, simultaneity dissolving into something more delicate than it seemed. A young mind, in the early 1900s, simply trusted this constancy, and the universe rearranged itself around that trust. Light slows down when it passes through glass. Inside that transparent stillness, photons interact with atoms again and again, delaying their forward journey ever so slightly. This is part of why a window pane, however clear, is not truly empty to light. The slowing is tiny, but it is enough to bend a beam, enough to make a lens focus the world into clarity. Water slows light as well, just a little more than glass does. This is why a straw in a glass of water appears to bend at the surface, as if reality itself had shifted. Light entering the water changes its pace, and with that change, its path curves. The whole effect is silent, invisible in the moment, yet written clearly into every rippling reflection. How much light slows in any material depends on something called the refractive index. Diamond bends light more than water. Water bends it more than air. Each substance holds its own quiet relationship with passing light, shaped by the density and arrangement of its atoms. It is a small, hidden signature, present in every material thing that light has ever touched. In empty space, though, the speed of light remains an unshaken constant, unaffected by anything nearby. No gravity, no motion, no passage of years changes this number in a vacuum. It is one of the few certainties the universe offers without hesitation. And from that certainty, Einstein found another, that mass and energy are bound together by the equation E equals mc squared, light's speed quietly holding the exchange rate between matter and energy. Let your breath find its own slow rhythm now. Notice the inhale arriving without effort, and the exhale growing longer, looser, less held. Each breath out can carry a little more weight from your shoulders, your jaw, the space between your brows. There is no need to breathe a certain way, only to let the next exhale be a fraction longer than the last, drifting you further from the day. Sunlight takes about 8 minutes to reach Earth after leaving the sun's surface. In that brief journey, photons cross 93 million miles of near emptiness, arriving as the warmth on your skin or the glow across a morning sky. Whenever you feel sunlight, you are feeling something that began its journey 8 minutes earlier, already old news by the time it lands. The sun you see is always the sun of 8 minutes ago. Since 1983, the meter itself has been defined by the speed of light. Rather than measuring light against a ruler, scientists reversed the logic entirely. A meter is now the distance light travels in a precisely fixed fraction of a second. Light became the standard, and every measuring stick in the world quietly adjusted to match it. The ruler now bends to light, not light to the ruler. Radio waves race across space at that very same speed as visible light. Though invisible to human eyes, radio signals are simply another kind of electromagnetic wave, cousins of light traveling the same cosmic highway. A message sent from a distant space probe moves at the same unhurried yet unbeatable pace as sunlight crossing a room. Whether it carries music, static, or silence, a radio wave never travels faster or slower than light itself. A universal speed limit governs everything in existence, and light travels right at its edge. No rocket, no particle, no signal of any kind has ever been observed exceeding this boundary. It is less a rule enforced from outside and more a structural feature of space and time themselves. The universe simply does not permit anything to outrun the pace light sets in empty space. As objects approach the speed of light, time itself begins to stretch for them. A clock aboard a ship nearing light speed would tick more slowly compared to one left behind on Earth. The closer that ship gets to light's pace, the more dramatic the stretching becomes, until time seems to nearly stand still at the threshold. This is not an illusion of instruments, it is how space-time actually behaves. Space and time are not two separate stages, but one interwoven fabric, joined by the constancy of light's speed. Einstein showed that distances in space and durations in time trade against each other, always keeping light's pace the same for every observer. Moving faster through space means moving slower through time, and moving slower through space means moving faster through time. Light speed is the quiet accountant balancing that ledger. High above Earth, GPA satellites carry atomic clocks that must be corrected for relativity's subtle effects. Because they move quickly and sit farther from Earth's gravity, their clocks tick at a very slightly different rate than clocks on the ground. Engineers built these corrections directly into the satellite systems, adjustments rooted in the constancy of light speed. Without them, location signals would drift by miles within a single day. Ole Romer, a Danish astronomer working in the 1670s, made the first real measurement of light speed. He noticed that eclipses of Jupiter's moon Io arrived earlier or later, depending on Earth's position in its orbit. From that timing difference, Romer reasoned that light itself must take time to cross space. His estimate was rough by modern standards, but the insight was genuinely groundbreaking. Light traveled, and its travel could be timed. Albert Michelson refined the measurement of light speed using a clever arrangement of rotating mirrors. Spinning an octagonal mirror at just the right speed, he could catch a beam of light on its return trip across miles of California landscape. His experiments, conducted in the late 1800s, brought the measured value remarkably close to what we accept today. Michelson's patient mirrors turned a cosmic mystery into a technical, almost delicate craft. A light year measures distance, not time, though its name suggests otherwise. It is the span that light crosses in one full year, moving through the emptiness of space at its unchanging rate. Astronomers use this unit because ordinary numbers grow too vast for stars and galaxies. 1 light-year alone stretches nearly 6 trillion miles, a distance the mind can name but never quite hold. Feel the weight of your body now, settling into the mattress beneath you. Let your feet grow heavy first, sinking a little deeper with each breath. Let that heaviness rise upward, through your legs, your hips, your chest, each part releasing into the surface that holds it. Your shoulders loosen, your hands grow still, and your head rests fully supported, as if the bed itself were gathering you in. James Clerk Maxwell discovered light speed hidden inside his own equations of electricity and magnetism. Working in the 1860s, he found that electric and magnetic fields could ripple together as waves, and when he calculated their speed, it matched the known speed of light exactly. This was no coincidence to Maxwell. Light itself, he realized, must be an electromagnetic wave born from the very forces that move compass needles and spark static electricity. Light moves as a wave of electric and magnetic fields, oscillating together as they travel through empty space. Neither field could exist without the other. Each generates its partner as it changes, locked in a continuous, self-sustaining dance. In a vacuum, this dance always unfolds at the same fixed rate. Radio waves, visible light, and gamma rays are all the same phenomenon, just tuned to different rhythms. Causality depends on light speed remaining an unbreakable ceiling. If a cause always happens before its effect, then nothing can outrun the signal that carries that cause forward. Physicists have shown that allowing faster than light travel would let effects arrive before their causes in some frames of reference that would unravel the orderly sequence the universe seems to depend on. Light's limit keeps before and after in their proper place. Information itself cannot outrun the light that might carry it. No message, no signal, no transmitted thought can cross space faster than light allows, no matter how clever the technology. This limit shapes everything from telephone calls to deep space missions. A command sent to a distant probe must wait, patiently traveling at light's fixed rate before any reply can return. Quantum entanglement links particles across vast distances, yet it never allows faster than light communication. When two entangled particles are measured, their outcomes correlate instantly, but no usable message travels between them. Physicists have confirmed this repeatedly. The correlation is real, almost eerie in its precision, but it carries no information a distant observer could decode ahead of light's own arrival. The cosmic microwave background carries light that has traveled since the universe's earliest ages. This faint glow, filling every direction of the sky, set out when the cosmos was only a few 100,000 years old. It has journeyed for nearly 14 billion years to reach our instruments today. Reading this ancient light lets astronomers see the universe's infancy, preserved in a whisper of radiation. The observable universe has a size fixed by how far light has managed to travel since everything began. Beyond that boundary, light simply has not had time to reach us yet, no matter how patiently we wait. This horizon grows outward every moment, but it can never encompass everything that may exist. Light's steady rate quietly draws the outer edge of what human eyes can ever witness. Black holes trap light not because light speed changes near them, but because gravity there grows overwhelming. Space itself curves so sharply around a black hole that every path, even one taken at full light speed, bends back inward past a certain boundary. Light keeps its familiar rate the entire time. Only the shape of space around it grows impossibly steep. The trap is geometry, not a broken speed limit. Gravitational lensing bends the path of light without ever changing how fast it travels. A massive galaxy or cluster warps the space around it, and light passing nearby follows that curve, arriving from an angle it never actually traveled in a straight line. Astronomers see doubled images, arcs, even glowing rings from this effect. The light speed stays exactly the same, only the road it walks grows crooked. No matter how fast you move, the speed of light measured beside you never changes. A traveler on a starship and someone standing still on Earth will each measure the very same value for light passing them by. This holds true in every frame of reference that moves at a constant velocity. It was this strange constancy, verified again and again, that convinced Einstein something deeper was happening to space and time themselves. Somewhere beyond the window, a low hum rises and fades, the kind of sound a house makes when it settles into night. Maybe it is wind moving through unseen branches, or a pipe cooling after the day's warmth leaves it. You do not need to name it. Let it arrive, hold its shape for a moment, and drift away again, the way sound always does when there is nowhere it needs to be. Galileo once tried to measure the speed of light using nothing more than 2 lanterns and the distance between hills. He and an assistant would uncover their lanterns and time how long the light took to be seen by the other. Of course, light moves far too fast for human reflexes or simple clocks to catch. His attempt failed, but it marked one of the first honest efforts to treat light speed as something measurable at all. In 1849, Armand Fizeau finally captured a real number for light speed using a rotating toothed wheel. He sent a beam through the spinning teeth toward a mirror kilometers away, timing exactly how fast the wheel needed to spin, so returning light slipped through the very next gap. From that spinning wheel and a distant reflection, he calculated a value remarkably close to the true speed of light in air. Not long after, Léon Foucault refined the measurement further using spinning mirrors instead of a toothed wheel. His rotating mirror reflected a beam toward a fixed mirror and back again, and the tiny shift in the returning light's angle revealed just how far the mirror had turned in that brief passage. Foucault's method was precise enough to show that light moves slower in water than in air, confirming a key prediction about light's wave nature. Modern lasers let physicists measure the speed of light with a precision earlier centuries could hardly have imagined. Instruments can now time light's passage over mere fractions of a second, with astonishing accuracy, confirming the same constant value again and again. This precision is so reliable that light speed itself became the very definition of the meter. What once took lanterns and spinning wheels now takes a laboratory built around silence and stable light. Some physicists have proposed that the speed of light might not have always been the same. These variable speed of light theories suggest that in the universe's earliest moments, light could have traveled at a different rate than it does now. It remains a minority view within cosmology, but it has persisted for decades as a serious alternative worth exploring, precisely because a few puzzles about the early universe still resist easy explanation. Varying speed of light theories were built to address puzzles that standard cosmology finds difficult to explain smoothly. One such puzzle involves regions of the universe, far apart and never in contact, that still share nearly identical temperatures and densities. If light once moved differently, perhaps distant regions were once close enough to share information before space stretched them apart. The idea offers one possible thread through an otherwise tangled cosmic knot. Variable speed of light theories were first proposed as an alternative to cosmic inflation, another idea meant to explain the universe's surprising uniformity. Inflation imagines a sudden, dramatic stretching of space in the universe's first instant. A changing light speed offers a different route to the same result, without requiring that explosive expansion. Neither idea has been proven, and both remain open threads in the larger tapestry cosmologists are still weaving together. João Magaijo works as a physicist whose name is closely tied to variable speed of light cosmology. He helped shape these ideas into something mathematically rigorous, not just a passing speculation. His papers explored what the early universe might have looked like if light once raced faster than it does now. He remains an active voice in this quiet corner of theoretical physics, still refining the models decades later. Andreas Albrecht joined this effort, helping develop variable speed of light models alongside Magijo. Together, they built frameworks where light's pace could shift in the universe's infancy, offering another path around a long-standing cosmological puzzle. Their collaboration produced technical papers that few outside physics ever read, yet the questions inside them echo through cosmology lectures even now. Two minds, working through equations, trying to imagine a universe with different rules at its very beginning. Certain variable speed of light models suggest that light moved faster during the universe's earliest fractions of a second. In that scenario, distant regions of space could have exchanged influence before the swift stretching of space pulled them apart forever. This faster early light offers one explanation for why the universe looks so evenly balanced across vast distances. It is a bold idea, held gently, tested against evidence that has not yet fully confirmed it. Let warmth begin at your feet now, spreading upward like sunlight, moving slowly across a floor. Feel it settle into your ankles, then rise gently through your calves, easing every small tension along the way. Let it pool behind your knees, then climb through your thighs, filling you with a low, steady heat. Let this warmth travel up your spine, into your chest, your shoulders, down through your arms to your fingertips. Rest here, warm and unmoving, as the glow reaches your face and settles behind your closing eyes. The fine structure constant, a small number that governs how light interacts with matter, might hold clues about whether light speed has ever shifted. If this constant changed over cosmic time, it could hint that the speed of light itself was never perfectly fixed. Physicists study ancient starlight for tiny signatures of such change. So far, the number holds remarkably steady across billions of years, but the search for the faintest wobble continues. Astronomical spectra, the fingerprints light leaves as it passes through gas and dust, are studied closely for hints that physical constants might not be perfectly fixed. Each spectral line carries information about the conditions under which it was emitted, sometimes billions of years ago. Astronomers compare these ancient patterns to the ones measured in laboratories today. Any subtle mismatch could suggest that something fundamental has shifted across cosmic time. Quasar light, born from some of the most energetic objects in the universe, travels for billions of years before reaching our telescopes. Astronomers examine this ancient light for signs that fundamental constants, including the speed of light, might have varied along the way. The spectra from these distant beacons are read like long letters sent across cosmic time. So far, the letters describe a universe whose laws have stayed remarkably consistent. No experiment performed so far has confirmed that the speed of light has ever changed. Every precise measurement, across laboratories and observatories alike, continues to return the same steady value. This does not close the question entirely, but it does anchor our confidence in light's constancy. The evidence, gathered patiently over generations, keeps pointing toward a universe where this particular rule holds firm. Distant supernovae, brilliant explosions marking the deaths of massive stars, offer another way to test light's constancy. Astronomers study how the brightness of these explosions rises and fades over time, comparing distant events to nearby ones. If the speed of light had shifted, these light curves might appear subtly distorted. Instead, the patterns match beautifully, reinforcing the sense that light's pace has remained unchanged across enormous stretches of cosmic history. Atomic clocks, some of the most precise instruments ever built, are used to test whether fundamental constants remain truly stable over time. These devices measure time with such exactness that even the smallest drift would be noticeable. Researchers compare readings across years, watching for the faintest deviation. So far, the constants tied to light's behavior have shown no sign of wavering, holding steady with a precision that borders on the poetic. Whether the value of light speed has held steady across the entire history of the universe remains an open question for cosmology. Billions of years stretch behind us, and most of that time cannot be directly observed. Researchers examine the oldest light and the faintest signals for any trace of drift. The universe, so far, offers no confession either way, only quiet consistency wherever we look. Doubly special relativity is a framework that allows the speed of light to remain the same for every observer, while also fixing a smallest possible length in nature. It builds on Einstein's original insight, but adds another unchanging quantity alongside it. Physicists developed this idea to explore what happens at the tiniest scales, where ordinary rules begin to strain. The universe, in this view, keeps its speed limit while gaining a second kind of constancy. Certain alternative theories of gravity make room for a speed of light that shifts depending on conditions in space. These frameworks depart from general relativity, offering different mathematical rules for how light behaves near mass and energy. Physicists build them carefully, testing whether they still match what telescopes and clocks observe. Most remain speculative, gentle threads of possibility woven beside the sturdier fabric of established physics. The horizon problem describes a puzzle in cosmology. Distant regions of the universe share nearly identical temperatures, even though light has not had time to travel between them under standard assumptions. This puzzle helped inspire the idea of cosmic inflation, a rapid stretching of early space. It also inspired an alternative path, where the speed of light itself was different long ago, allowing distant regions to have once been in contact. Both ideas try to answer the same quiet mystery. Somewhere beyond the window, mist gathers low over unseen fields, drifting without hurry from one shape into another. It has nowhere it needs to be, and no shape it needs to keep. Let your breathing settle into that same drifting rhythm, rising and falling like mist over water. Your shoulders can loosen now, sinking a little further into the bed. There is only this slow unfolding, this soft dissolving, carrying you gently toward sleep. Einstein's equations of general relativity treat the speed of light as a fixed constant woven directly into their structure. If that value were allowed to shift, the equations themselves would need to be rewritten from the ground up. Physicists who explore this possibility must rebuild the mathematics carefully, checking that gravity, energy, and motion still fit together. It is delicate work, adjusting the foundations of a house while trying not to disturb the rooms already built above. The Planck length, the smallest meaningful distance in physics, is calculated using the speed of light alongside two other fundamental constants. If light speed were different, this tiniest of scales would shift as well, changing our sense of where ordinary space ends and something stranger might begin. It is a small number woven from big ideas, and altering one part ripples quietly through the whole calculation. Cosmic inflation explains why distant regions of the universe look so similar by proposing a sudden dramatic stretching of space in its earliest moments. A variable speed of light offers a quieter alternative, suggesting that light itself once moved fast enough to connect those distant regions without any stretching at all. Either idea, if true, would answer the same old question in a very different voice. Where inflation solves the horizon problem by expanding space itself, a changing speed of light offers a different kind of solution, letting light race ahead fast enough to link distant corners of the early cosmos. Both approaches try to explain how far-flung regions ended up so alike. Physicists weigh these ideas against each other patiently, testing which one fits more comfortably with everything else we already know. Atomic energy levels, the precise steps electrons occupy within atoms, are calculated using formulas that include the speed of light. A shift in that value would nudge these levels ever so slightly, changing the exact colors atoms absorb and release. Since starlight itself is read through these very colors, even a small change could ripple outward into how we interpret the light arriving from distant skies. Nuclear fusion inside stars depends on a delicate balance of forces, and several of those forces trace back to constants tied to light speed. The rate at which hydrogen fuses into helium relies on how strongly particles repel and attract one another. Calculations threaded with the value of C. Change that value, and the furnace at a star's heart would burn differently, altering how long stars live and how brightly they shine. Electromagnetic interactions, the forces binding electrons to atoms and light to matter, carried the speed of light woven into their strength. A different C would shift how strongly charged particles pull on each other, subtly rewriting the rules that hold ordinary matter together. Chemistry, magnetism, even the spark of a struck match, all lean on this same underlying number, more foundational than most of us ever pause to notice. Atoms owe their size, in part, to quantum electrodynamics, the theory describing how light and matter exchange energy. Buried within its equations sits the speed of light, shaping how tightly electrons orbit their nuclei. A faster or slower C would nudge that balance, making atoms either shrink or swell ever so slightly, changing the invisible architecture that every solid object around you is quietly built from. The Bohr radius, a simple measure of how far an electron typically sits from its nucleus, depends directly on the speed of light through the formulas of quantum theory. Adjust that speed, and this radius shifts too, stretching or shrinking the basic scale of atoms everywhere. It is a strange thought that something as vast as light's velocity reaches all the way down into the smallest architecture of matter. Starlight's color depends on temperature, but the physics translating heat into visible light runs through constants that include the speed of light. A different C would shift how efficiently stars radiate energy, changing the balance of blue, white, and red across the night sky. The familiar palette of constellations, painted over billions of years, might have looked entirely different under another value for light speed. Let your jaw loosen now, just a little more than before. Feel the small muscles around your eyes give up their hold, eyelids growing heavier with every breath you release. There is a darkness behind them that asks nothing of you, no shape to follow, no light to track. Let your face rest completely, as if it has finally set down something it did not know it was carrying. Photons, the particles of light, carry energy tied directly to their wavelength, and that relationship depends on the speed of light. A variable C would shift the wavelength of every photon leaving every star, every lamp, every distant galaxy. The very colors astronomers rely on to read the universe would no longer mean quite the same thing. They mean tonight, under our current, steady value of light speed. Redshift, the stretching of light toward longer wavelengths as galaxies recede, is one of astronomy's most trusted tools, but its interpretation assumes the speed of light has never wavered. If C had changed across cosmic history, some of the redshift we measure might reflect that shift rather than motion alone. Untangling the two possibilities remains a careful, ongoing puzzle for those who study the universe's expansion. Distance in astronomy is often measured by timing how long light takes to travel, a method that only works if light speed has always been the same. Every calculation of how far a star or galaxy sits from Earth leans on this quiet assumption. It has held up under every test performed so far, yet it remains, in the deepest sense, an assumption rather than a certainty. A change in light speed, however small, would ripple through every distance calculation built upon it, from the closest stars to the farthest galaxies. Maps of the cosmos, drawn under one value of C, might look noticeably different under another, entire scales of space quietly redrawn. It is a reminder that even our grandest measurements rest on foundations we simply trust to remain still. Dark energy, the mysterious force stretching the universe apart, remains one of cosmology's deepest puzzles. A shifting speed of light could produce effects that look remarkably similar to what dark energy seems to cause, without requiring any new hidden force at all. Researchers exploring this idea wonder whether some of what we attribute to a mysterious push might instead trace back to light's own changing pace. Dark matter, the invisible mass astronomers infer from galaxy rotation, has never been directly observed, only felt through its gravitational fingerprints. Certain theoretical models propose that a varying speed of light across cosmic history could account for these same fingerprints. It remains an open question whether such models could ever fully replace the need for an unseen substance filling the space between stars. Critical density describes the delicate threshold deciding whether the universe expands forever or eventually collapses inward. This threshold depends on the value physicists assign to light speed within their equations. Adjust that speed even slightly, and the entire balance point shifts, changing what astronomers would consider a universe destined to expand endlessly versus one destined to fold back on itself. Big Bang nucleosynthesis, the process that forged the universe's first light elements, unfolded within the first few minutes after the beginning. Physicists calculating how much hydrogen and helium should exist rely on light speed remaining fixed throughout that fiery interval. Even a brief variation during those early minutes could have shifted the resulting proportions astronomers now measure in ancient gas clouds. Standard candles, stars, and explosions whose brightness astronomers already understand allow distances across the universe to be measured with remarkable confidence. This method assumes light has always carried its brightness across space at one unwavering pace. Should that pace have drifted over billions of years, the candles once trusted as reliable rulers might quietly mislead every measurement built upon them. Calculating the universe's age depends on tracing light's journey backward through billions of years of cosmic history. Every equation assumes that light's pace has remained the same the entire way. If that pace had shifted even briefly somewhere along that long journey, our careful estimate of the universe's age could be subtly, invisibly off, resting on an assumption no one can fully verify. Notice your breath moving on its own, without effort, the way it has all through this long, unhurried listening. Feel the exhale grow a little longer each time, stretching further into the dark before the next breath quietly arrives. There is no need to guide it. Let each exhale carry a little more of the day away until the breath itself feels like the only sound left in the room. Mass and energy, bound together by light speed squared in Einstein's famous equation, would relate to each other very differently under a faster light. Even a modest increase in that speed would dramatically inflate the energy locked inside every particle of matter. A single grain of sand, under such a change, would suddenly represent an almost unimaginable reservoir of stored power. Stars maintain a careful balance between gravity pulling inward and fusion pushing outward, a balance tied closely to light's pace within their cores. A faster light speed would tip that balance, allowing fusion reactions to race ahead more quickly than gravity could restrain them. Stars under such conditions would burn through their fuel far sooner, living bright, hurried lives instead of long, steady ones. Image parts, image prompts, a glowing star's core rendered as fast-swirling luminous plasma, bright fusion sparks accelerating, warm, intense golden light, dynamic yet serene cosmic close-up. Was-up narration, nuclear binding forces hold the particles within an atom's nucleus tightly together, resisting the atom's nucleus tightly together, resisting the natural push of positive charges wanting to fly apart. These forces depend, in part, on relationships involving light speed. A faster light would loosen that grip, weakening the bonds holding nuclei intact, leaving atoms across the universe just a little less firmly held together than they are tonight. Binding forces inside every atomic nucleus keep protons and neutrons pressed together despite their mutual repulsion. Physics ties the strength of that grip to relationships involving light's pace. A faster light would loosen this hold, softening the forces that keep nuclei whole. Matter across the cosmos would find itself held less firmly than it is tonight, its innermost structure a touch more fragile. Atomic nuclei already balance on a narrow edge between stability and decay. Weakened binding forces would push many of them past that edge entirely. Elements that once lasted for billions of years might become unstable within moments. The periodic table itself, as we know it, could shift toward simpler, lighter forms, unable to hold their heavier arrangements together. Gravity's pull, though it feels like an unshakable law, hides a dependence on light speed within its equations. A faster light could thin that pull, loosening the invisible leash that holds moons to planets and planets to stars. Massive bodies would feel less compelled to draw others toward them, and orbits everywhere would begin to drift outward ever so slightly. Chemical reactions, the small exchanges of electrons that rust iron and burn wood, unfold at rates tied to constants linked to light. Increase that speed, and these exchanges would happen faster, driven along by shifted energy levels. Fires would burn quicker, reactions would finish sooner, and the chemistry underlying every living cell would race ahead of its familiar rhythm. Radioactive decay follows a steady, ancient rhythm, each unstable atom releasing energy on its own timetable. A faster light speed would tighten that timetable considerably. Isotopes that decay over thousands of years might instead unravel within decades. The careful clocks scientists use to date fossils and rocks would suddenly run at an unfamiliar, hurried pace. Time dilation, the stretching of moments experienced by travelers nearing light speed, depends entirely on how close they come to that boundary. A faster light would push that boundary further away, so ordinary speeds would produce less noticeable stretching. A traveler moving at speeds that once caused dramatic time differences would barely notice any difference at all in such new conditions. Distant worlds, reachable today only after decades or centuries of travel, would draw closer if light itself moved faster. A ship approaching that higher limit could cover distances once thought impossible within a single human lifetime. Voyages to nearby stars might shrink from generations to mere years, turning journeys once reserved for imagination into something almost within reach. Messages between planets currently carry a delay, measured in minutes or hours, the unavoidable cost of light's steady pace. A faster light would shrink that delay considerably. Conversations between Earth and Mars, now separated by long pauses, could happen almost as quickly as talking across a room. The solar system would feel, for the first time, genuinely connected in real time. Let your shoulders sink a little further into whatever is holding you right now. Feel the weight of your arms settle, heavy and unmoving, as though the mattress has learned the shape of you. Your legs feel dense now too, pressed down by nothing more than gravity, and the day finally letting go. Let that heaviness travel up through your chest, your neck, your jaw, until even your eyelids feel too heavy to consider opening. There is only the weight of you, resting fully, sinking a little deeper with every breath. Orbits that keep planets circling their stars rely on a balance struck long ago between gravity and momentum. A sudden rise in light speed could throw off the constants underlying that balance in an instant. Planets might find themselves suddenly moving too fast for their orbits to contain them, drifting away from the stars that once held them close, adrift in a sky far emptier than before. The observable universe, vast beyond ordinary imagining, is bounded by how far light has managed to travel since the Big Bang. If light suddenly moved faster, that boundary could leap outward in an instant, revealing regions once hidden beyond reach. Galaxies never before glimpsed might flicker into view all at once, the edge of everything we can see expanding faster than any telescope could track. Waves of gravity ripple outward from moving masses at the same pace light travels, according to general relativity. A faster light speed would mean gravitational influence itself moves quicker across space. Distant stars might tug at each other with less delay, their gravitational conversations arriving sooner, subtly reshaping how galaxies feel one another's presence across the dark. Fields of electricity and magnetism are woven together by constants tied closely to the speed of light. A change in that speed would alter how strongly charges attract, repel, or spark across a gap. Magnets might cling harder or looser, currents might surge differently, and the invisible forces holding circuits together would shift in ways no engineer had planned for. Every circuit humming quietly inside a phone or a satellite depends on timing governed partly by light's steady pace. A faster sea would throw off those calculations, making processors misfire or signals arrive out of step. Devices built for one speed of light might stumble, their tiny electrical pulses no longer matching the rhythm the world was designed around. Within the body's wiring, nerve signals travel through electrochemical waves, not light itself, yet the constants shaping those waves trace back to deeper physics tied to C. A shift in light speed could ripple through those foundational numbers, altering how quickly a signal moves from fingertip to brain. Reflexes, thought, even the felt sense of time might shift in ways too subtle to name. Overhead, satellites hold their positions through calculations that assume light speed never wavers. Global positioning depends on timing signals accurate to fractions of a second, each one built on a constant considered unshakable. A faster sea would throw those calculations off, and a location marked on a map might drift quietly away from where a traveler actually stood. Visible light spectrum, the narrow band of color the human eye can perceive, depends on the relationship between wavelength and speed. If light suddenly moved faster, wavelengths might stretch or compress across that band, shifting which colors reach the eye at all. Sunsets could shift their hue, and the ordinary rainbow might arrive looking like something never seen before. Deep in nebulae, gravity slowly pulls gas and dust together until pressure and heat ignite new stars. The physics governing that collapse touches constants linked to the speed of light. A faster sea might quicken or delay ignition, changing how swiftly clouds birth their stars. Nurseries that once took millions of years to bring a star to life might work at an entirely different pace. A supernova's blast releases in moments the energy a star spent its lifetime storing, governed by nuclear processes tied to fundamental constants. A faster speed of light could intensify that release, making stellar deaths even more energetic than the ones we know. The light from such an explosion might carry more power outward, briefly outshining entire galaxies by an even wider margin. Somewhere beyond this room, a low hum rises and fades, the kind of sound a house makes when it settles into night. Perhaps it's the wind finding a gap in a window, or a distant hum of traffic thinning into silence. Let it arrive without asking anything of you. Let it pass through the room and out again, leaving nothing behind but stillness. You don't need to follow where it goes. You can simply notice it fading, the way a thought fades, the way the day is fading now, until there's only the dark and your breath and the soft space left behind when a faraway sound has gone quiet. A train moving through a slowed universe would seem to gain weight as it sped up, not just in feeling but in measurable fact. Mass tied to motion depends on how close a speed comes to the light limit. With a lower ceiling, even a bicycle or a thrown ball could edge toward that limit, and its resistance to further push would grow noticeably heavier. Clocks on a slow walk might drift out of step with clocks left behind on a bench. Time dilation, ordinarily reserved for spacecraft and particle accelerators, would creep into daily errands. A person jogging to catch a bus could return home moments younger than a sibling who stayed seated, the difference finally large enough to notice without instruments. Objects gliding across an ordinary kitchen table would seem to resist their own motion more than expected, mass swelling as speed rose even at the modest velocities of daily life. A rolling apple might feel unexpectedly stubborn to stop. The strange relativistic weight once hidden safely near light speed would spill into rooms, drawers, and hands. Deep inside every atom, protons and neutrons cling together through a force whose strength depends partly on the constant we call light speed. Lower that constant, and the glue holding nuclei together would loosen. Elements that once felt permanent might begin to feel provisional, their cores held by a weaker embrace than the one that built the periodic table. Matter itself, so reliable underfoot and in hand, depends on constants working together in careful proportion. A lower speed of light could tip that proportion, letting nuclei that were once stable begin to falter. Nothing about a chair or a stone would look different at first, yet somewhere in their atomic hearts, a quiet unraveling might begin. Deep within the sun, hydrogen fuses into helium through a chain of reactions tuned to the exact value of light speed. Slow that value, and the energy released with each fusion event would shrink. Stars everywhere would burn with less intensity, their furnaces still lit, but their flames noticeably dimmer than before. Sunlight, reaching Earth, carries the output of countless fusion reactions happening far below the surface of our star. A slower light speed would mean less energy escaping with each of those reactions, and over time, the sun's glow could fade. Mornings might arrive a little grayer, the warmth on skin a little less certain. A phone call across a room, ordinarily instant to human senses, would begin to carry a perceptible pause if light itself moved slower. Signals traveling through wires and air depend on that speed for their swiftness. Even short distances, once crossed without a thought, would start to feel like they held a small, unfamiliar delay. Overhead, a constellation of satellites keeps time with extraordinary precision, using light speed as part of their exact calculations. Lower that speed, and every calculation built upon it would drift out of alignment. Positioning systems relying on those signals might lose their accuracy altogether, leaving maps and directions quietly unreliable. Eyes and brain work together through nerve signals and light, both bound by the same universal speed. A slower light speed could stretch the gap between seeing something and truly perceiving it. A hand reaching for a cup might seem to move just ahead of its own image, a small, dreamlike stutter written into ordinary sight. Let warmth begin at the crown of your head, a low golden ease settling into your scalp and temples. It moves without hurry down through your jaw, releasing whatever the day held there. Down through your shoulders next, loosening what has been carried too long. Into your chest, your arms, your open hands. Down through your hips, your legs, your feet, until every part of you rests in that same warm hush. There is only this warmth now, and the dark and the slow going under. Storm skies already show a gap between the flash of lightning and the sound that follows, since light crosses that distance in a breath, while sound lingers behind. A slower speed of light would widen that gap even further, stretching the flash's arrival ahead of the thunder's low roll. Watchers might see brightness fill the horizon long before any rumble reaches their ears, the storm's light arriving as if from some slightly more distant place. Sunlight carries a particular color temperature, a warmth or coolness tied to how its photons distribute their energy. Lower the speed of light, and that balance could shift, since photon energy connects to fundamental constants including light speed. Daylight might lean redder, gold deepening into amber even at midday. A field bathed in that altered light could look perpetually lit by late afternoon, warm and low. Nearby stars might appear brighter under a slower light speed, astronomers speculate, since altered constants could change how much energy each photon carries and how starlight disperses across distance. A dimmer, farther sun might seem to burn a touch closer, its glow pressing gently into the night sky. Constellations already familiar could take on an unfamiliar luminous weight. Chemical bonds hold atoms in careful balance, an equilibrium shaped partly by the fine structure constant, which depends on the speed of light. A decrease in that speed could loosen the balance, weakening the forces that keep electrons in their shared orbits. Molecules ordinary and unremarkable, water, wood, skin, might grow subtly less stable, their architecture no longer quite as firm. Photons born in the sun's core do not travel outward directly. They wander for tens of thousands of years, bouncing through dense plasma before finally escaping. A slower speed of light would stretch that inward journey even longer, delaying every photon's release into space. The sunlight reaching a garden this afternoon would carry an even older story from deep within the star. Galaxies hold together through gravity's steady pull across vast distances. Physics ties the propagation of that pull to the same constant governing light. A reduced speed of light could deepen gravity's grip, cosmologists suggest, binding galaxies more tightly and drawing their stars into closer, more crowded formations. Spiral arms might curl in a little nearer to their centers than before. A black hole's boundary depends on both its mass and the speed of light, since that boundary shrinks as light speeds up and swells as it slows. A slower speed of light could make every black hole's event horizon expand, stretching its shadow wider across surrounding space. Familiar giants at galactic centers might loom larger still, their dark reach extending outward. The cosmic microwave background carries a faint afterglow of the early universe, cooled over billions of years to a temperature just above absolute zero. A decrease in the speed of light would alter the relationship between that radiation's frequency and its measured warmth, cosmologists note, changing the number etched into every reading of the sky's oldest light. The background hum of creation might read a little warmer or a little colder than it does now. Distances across the cosmos rest on assumptions about how far light has traveled since the beginning of time. If the speed of light had once been slower, cosmologists speculate, past calculations built on today's constant might have underestimated how far ancient light truly needed to travel, expanding humanity's sense of the universe's true scale. The night sky could hold more distance than anyone has yet imagined. Radioactive decay depends on nuclear forces whose strength ties subtly to the speed of light. A drop in that speed could shift decay rates dramatically, physicists note, changing how quickly unstable atoms release their stored energy. Carbon dating, medical isotopes, and the slow cooling of planetary cores could all unfold at unfamiliar tempos. Elements considered stable today might begin transforming at a different pace entirely. Somewhere in the dark, an ember dims by degrees, its glow drawing inward until only a faint red memory remains. Let your breath match that fading, each exhale carrying a little more of the day away. There is no need to chase its light any further tonight. Let your shoulders settle deeper into the mattress, your eyelids heavier than the ember's last glow. Rest inside that fading, and let sleep gather you in. Space-time itself might not survive an abrupt change in light speed. Physicists studying general relativity have noted that the geometry linking space and time depends on light's constancy to remain smooth and continuous. An instantaneous shift could tear that fabric, producing ruptures where distance and duration no longer connect in familiar ways. Such a rupture remains purely theoretical, a mathematical curiosity, rather than an observed event. Energy conservation stands as one of physics' most trusted principles, tested across countless experiments and untouched by exception. An instantaneous change in the speed of light could break that principle outright, since energy and light speed are woven directly into the same equations. Cosmologists regard this possibility as deeply troubling for any serious theory, more a warning sign than a prediction. It suggests that such sudden shifts, if they ever occurred, would need entirely new physics to explain them. Certain theoretical models allow physical law itself to differ from one region of space to another. A changing speed of light in these frameworks could create pockets where familiar constants no longer apply, isolated bubbles governed by their own quiet rules. Within such a region, chemistry, gravity, even the passage of time might behave in ways foreign to their surroundings. No evidence for these bubbles exists, though the mathematics describing them remains internally consistent. Physicists exploring extreme gravity have proposed that light speed might shift subtly near a black hole's event horizon. Under such intense curvature, the usual constancy of light could bend into something more flexible, its pace tied to the surrounding gravitational field. Observers falling toward the boundary might measure a rate unlike anything seen in open space. This idea remains untested, a possibility drawn from theory rather than direct observation. Beyond our own universe, speculative physics imagines constants that differ entirely from ours. The speed of light in these frameworks might take on entirely different values within neighboring universes, each with its own internal consistency. A universe with a faster light speed could burn through its stars in a fraction of the time ours requires. Another, slower still, might stretch its entire history across timescales beyond comprehension. Multiverse theories, born from certain models of eternal inflation, describe an endless foam of separate universes drifting apart from one another. Each bubble in this picture could settle into its own value for the speed of light as it cools from a shared origin. Some bubbles might freeze into rules resembling our own, while others diverge into forms unrecognizable. No observation yet reaches beyond our single bubble to confirm any of this. The strong nuclear force holds every atomic nucleus together, binding protons and neutrons against their mutual repulsion. A changing speed of light could alter the strength of that force, since the equations describing nuclear binding depend on light speed as a hidden variable. Atoms across the universe might hold together more loosely or more fiercely than the ones familiar to us now. Entire elements could become unstable, while others might never have formed at all. String theory imagines the universe woven from dimensions curled too small for any instrument to detect. Variable light speed theories intersect this framework by suggesting that changes in those hidden dimensions could reshape the constants we observe, including the speed of light itself. A universe with differently sized extra dimensions might experience an entirely different value for c. The mathematics remains elegant, though far removed from anything measurable today. String theory offers many possible mathematical universes, each shaped by how its hidden dimensions curl and fold. Within a number of these models, fundamental constants like light speed are not fixed, but emerge from the geometry itself. As that geometry shifts across cosmic history, the value of light speed could shift alongside it. The mathematics allows for such motion, though nothing yet ties it to anything we can observe. Protons are thought to be extraordinarily long-lived, surviving perhaps longer than the current age of the universe many times over. A shifting light speed would ripple through the equations that predict just how long a proton endures before decaying. Slight changes to that hidden constant could stretch or shorten those unimaginable timescales. No decay has ever been observed, so the number remains theoretical, resting quietly within the mathematics. Let your jaw loosen, just slightly, as though it forgot what effort felt like. The muscles around your eyes release their hold, one small thread at a time. Behind your closed lids, there is only a soft, dim field, wide and unmarked. No shapes ask anything of you there. Let your face rest the way still water rests, holding nothing, asking nothing, simply settled into itself. Loop quantum gravity approaches the universe differently, describing space itself as woven from tiny discrete loops rather than a smooth continuum. In several versions of this framework, light speed is allowed to vary at scales far smaller than anything ever measured. Near the smallest imaginable lengths, the usual rules may loosen their grip. Whether this happens in reality remains an open question, one still waiting on evidence too fine for current instruments. Quantum foam describes a hypothetical texture to space at its smallest scale, a churning fabric where geometry itself trembles. Speculative physics sometimes ties a wandering light speed to this foam, imagining photons jostled ever so slightly as they pass through its microscopic turbulence. Over vast distances, these tiny disturbances might average into something measurable, or they might cancel away entirely. The idea remains graceful, resting mostly within equations rather than observatories. Vacuum energy fills empty space with a faint, persistent hum of activity, one that current theories struggle to fully explain. A changing light speed could feed into that hum, nudging the delicate balance that keeps vacuum energy stable across the universe. Even a small shift might ripple outward, altering how empty space itself behaves. Physicists studying this connection describe it as fragile, dependent on constants intertwined more deeply than expected. In the earliest fractions of a second after the Big Bang, conditions were unlike anything that followed. Some theorists propose that light speed itself may have flickered briefly during that primordial moment before settling into the steady value we know today. Such a flicker, if real, would have left its imprint deep within the universe's oldest structure. No confirmed trace of it has yet been found, though the search continues patiently across cosmic data. Space itself can curve, bending gently under the presence of mass and energy, as general relativity describes. Certain cosmological models propose a link between that curvature and a wandering light speed, suggesting the two might rise and fall together across cosmic history. A universe curving more sharply might, in these frameworks, carry a different value for c. The connection stays theoretical, woven from elegant equations rather than confirmed data. Across decades of storytelling, science fiction has often dreamed past the light barrier entirely. Starships in these tales leap between stars in moments, faster light allowing crews to bypass the vast emptiness between worlds. Such stories borrow the language of physics while drifting comfortably into imagination. They offer no evidence, only a mirror for our longing to reach distances that otherwise remain unreachable within a single lifetime. Warp-drive concepts, born from theoretical work-bending general relativity into new shapes. Imagine compressing space ahead of a ship and expanding it behind. In some versions, this reshaping is described as altering the effective speed limit within a small, local bubble of space. The ship itself would remain still relative to its own bubble, while the bubble moves freely through the wider universe. Such ideas remain deeply speculative, resting on exotic energy no one has ever found. Distant listeners, out among the stars, might tune their instruments to a light speed they assume never wavers. If C shifted, any message timed against that assumption could arrive scrambled, arriving too early or lingering too long en route. A signal built to align with a fixed rhythm could fall out of step entirely. Whole networks of cosmic communication, however advanced, would depend on the same constant holding true everywhere. Voyages between stars rely on light speed to calculate how long a crossing should take. A ship setting out toward a distant sun trusts that the light guiding its measurements moves at the same pace throughout the journey. If that pace wavered along the way, arrival times could stretch or compress unpredictably. Explorers might leave with careful calculations and arrive centuries earlier or later than any chart foretold. Storytellers sometimes imagine societies clever enough to bend light's limit itself, carving out small pockets where the old rules no longer apply. In these tales, an advanced civilization tunes the vacuum like an instrument, coaxing light to move faster within a chosen boundary. Beyond that edge, the ordinary universe continues unchanged. It remains a device of imagination, a way of asking what mastery over light might someday mean. Notice your breath now, moving on its own, in and out, unhurried. Let each exhale grow a little longer than the one before it. There is no need to count them, only to feel how each one arrives and leaves in its own time. With every longer exhale, the shoulders settle a little further into whatever is holding you. Let the breath carry you down, breath by breath, into rest. Beyond storytelling, a few theorists have wondered whether a civilization far older than ours might notice a light-speed drift we cannot yet perceive. Over millions of years, tiny shifts could accumulate into something measurable, an anomaly a watchful observer might catch. Such detection would require timescales far beyond a single lifetime or even a species' recorded history. It remains a thought experiment, resting on a patience longer than our own existence. Somewhere ahead, a future experiment might place ultra-precise clocks near massive bodies, watching for any flicker in how fast light travels through curved space. Near a neutron star or black hole, gravity grows strong enough that subtle effects could, in principle, surface. No instrument yet built has the precision required. The idea waits for technology not yet invented, a question held in reserve for a future generation. Physicists speculate that quantum gravity, the still unfinished theory joining gravity to the quantum world, might reveal that light's speed limit is not as fixed as it appears. At scales smaller than any experiment can reach, space-time itself may behave differently, and the constant we rely on could emerge only as an approximation. No complete theory yet exists to confirm this. The idea lives at the frontier where physics runs out of firm ground. A slowing light speed in one line of speculation could serve as a signature of a universe running down. If the value of c crept lower across immense stretches of time, older starlight might arrive shifted in ways that hint at fatigue rather than mere distance. No observation has shown such a trend. It stays a poetic possibility, a way of imagining the universe growing weary, the way any long journey might. An accelerating light speed, by contrast, has been imagined as a sign of renewal, as though the universe were quickening rather than fading. In this speculative picture, a rising sea might accompany some deeper reawakening within the cosmos, a fresh burst of energy after eons of quiet. Nothing in current data supports this either. It remains a mirror image of the slowing scenario, equally unproven, equally born from wonder rather than evidence. A theoretical scenario paints a version of humanity waking each morning to a light speed subtly different from the day before. Shadows might lengthen unexpectedly, distant clocks might drift from local ones, and the sky's old arithmetic could seem to shift beneath careful eyes. Such a world exists only within thought experiments. Ours has shown no such change, its light speed holding steady across every measurement ever taken. A hypothetical experiment could measure C shifts using ultra-precise atomic clocks placed far apart and compared over long stretches of time. If light speed drifted even slightly, the timing between distant ticks would slowly fall out of step. Engineers building today's most sensitive clocks already chase precision as fine. No drift has ever been found. The clocks keep their perfect agreement night after night, year after year. Cosmic light speed changes have been imagined as an explanation for gaps in stellar formation, moments in the universe's early history when fewer stars seem to have ignited than expected. A shifting sea might have altered the pressures and temperatures needed for clouds of gas to collapse into new suns. The idea is speculative, resting more on curiosity than confirmation. Astronomers studying those quiet eras still favor simpler causes, like uneven density in the primordial gas. Philosophical debates ask whether physical constants can be truly constant forever, or whether permanence itself is an assumption borrowed from human experience. A number fixed for 14 billion years might still be changing on scales too slow for any instrument to notice. Philosophers of science point out that constancy is something we infer, not something we can fully prove. The question drifts beyond physics into how certainty itself is built. Ultimately, no evidence yet confirms that the speed of light has ever changed. Every measurement, from ancient eclipses of distant moons to modern lasers bounced across laboratories, has returned the same steady number. The universe, as far as anyone can tell, has kept its promise of light traveling at exactly this pace since the beginning. And so, the number stays fixed, one of the few things vast enough to be trusted completely, while everything else, including you, drifts gently toward rest.